Today we are going to take a look at the complex number system. So complex numbers are numbers that are rational or irrational, but they do have a complex or imaginary component to them. So when we're working with complex numbers, we're also using this imaginary unit I, which represents the square root of -1. So complex numbers are based on numbers that have a square value of -1. So a number times a number is equal to -1, essentially. But that makes it very complex when you're trying to take the square root of a number. So, for example, if I look at the square root of 16, well, the square root of 16 is 4. So 4 times 4 equals 16, or -4 times -4 equals 16. So you have two identical numbers. When multiplied will give you your value. That becomes very complicated when you throw in a negative number. So for example, -16. What is the square root of -16? Well, +4 times -4 gives you -16, but that totally nullifies the definition of what a perfect square is, because a perfect square simply means that two identical values must be multiplied to give you that product. But because 4 and -4 are not identical, it is not technically a square root. So that's why it makes it very complicated. That's why we call it the complex number system, because we're working with this complex idea of taking a square root of a negative number. This does happen in real world scenarios where you're measuring distance, or you're looking at values that don't technically cross the x-axis but don't need to cross the x-axis in order to have a real solution. So for example, like a roller coaster, you never actually want a roller coaster to come in contact with the ground, i.e. the x-axis, because that would just be really tragic and a hot mess. So we have this complex number system, mostly done with dealing with distance and things like that. So when we have to separate that, we include a complex or imaginary component. So we would simply break down -16 into the square root of -1 times the square root of 16. Well, now I have a real component that I can work with. I can work with the number 16. I know that in its entirety, it's still going to be imaginary. It's still going to be complex because it does have the square root of -1 associated with it. But now that I have 16 by itself, I can break that down. So the square root of 16 is 4, and the square root of -1 is replaced with the letter I. So I have a total value of 4i. So the square root of -16 is 4i. So that's kind of how that I comes into play, and why that square root of -1 is very important to separate out from the rest of your values. Complex numbers do take on the form a plus bi, where a represents a real component, nothing to do with an imaginary value whatsoever. This could be a number, a decimal, a fraction, a radical. It is completely separated from your complex component. Your complex component does include that imaginary value. So for example, in the last one, 4i would be considered our imaginary part of our complex number. If we had, for example, a random boring number, let's say 2. 2 is a real value. It does not have an I or a complex component, so 2 would be considered my value for A. When we simplify radicals, which we're going to have to do when we look at multiplying and dividing, we need to be able to simplify radicals down into their absolute most simple form while taking care of the negative value at the same time. So I've got this example, square root of -18. If I was to separate that out and use simply my 18 and my square root of -1, so separating that I value away from your 18, you can break your 18 down. So what I like to do is prime factorization. So that means breaking the values down into their absolute prime numbers, or breaking them down till you can't break them down anymore. So factors of 18 are 2 and 9. You could have started with 3 and 6. When you're working with radicals, it doesn't really matter where you start as long as you continue breakdown. because at the very bottom, all of your prime factorizations, no matter what initial factor you started with, all your prime factors are going to match at the end. So if I started off with 3 and 6, when I get done, I'm going to have 2, a 3, and a 3 as a prime factor. And my square root of negative 1 turns into the letter I, and it is separated from my radical. So when I'm simplifying radicals, I'm looking for identical twin values. So in this particular example, I have a set of 3's. The first number will come out of the radical, the second does not. So in this particular case, the 3 comes out of the radical, the second 3 kind of just disappears. We don't use it. We're only looking for twins that can come out of the radical, and only one twin is represented. And so when you have values left over like 2, here it doesn't have a twin, it's a standalone number. It does get left behind in the radical. So the square root of 18 reduces down to 3 times the square root of 2. And we also have to include our imaginary component. And it's not technically a variable. It kind of gets treated like one, but it is technically not a variable. But when we multiply this out, we will have 3i times the square root of 2. And that is the simplified version of the square root of negative 18. And that will come into play when we look into multiplying and dividing complex numbers and looking at conjugate values. So just as a kind of a reminder of how to simplify using that I. Well, complex are also able to be graphed. However, they're not graphed on a regular XY plane because they are not a regular XY coordinate. They are a complex number. So our complex numbers have a complex grid. On the x-axis is located all of my real values, or my A values here. And my imaginary contains my complex portion of my number. And so I've got the example 3 minus 2i. So here's my example. And when I graph this, I'm going to kind of treat it like an ordered pair, in that I'm traveling left to right along the horizontal axis first, and then up and down on that vertical axis secondly. So because my real component here is a positive 3, on my real axis I will go to the right 3 units. My imaginary component is negative 2i, which means that I will go down 2 units. And so my complex number is graphed at this point right here on my graph in quadrant 4. So that is how complex numbers are graphed. We use this especially when we're looking at distances and things when they're plotted in various different kinds of planes. And we use this quite frequently in engineering, computer programming, things like that. But because complex numbers deal with distance, being able to plot this complex number is great and wonderful and fantastic, but it doesn't give me any kind of information as far as distance or length or any of that. So in order to measure out the distance and use that complex number for what it was developed for, we have the absolute value of a complex number. It's a little bit of a misnomer in that it's a play on the Pythagorean theorem, but it is used to measure distance from the origin. So when we think about absolute value, for example, let's say the absolute value of negative 5, we always just assume, oh, it's just a positive number. But absolute value is a measurement. So on a number line, if this is 0, negative 5 is on the left-hand side. The distance away from 0 is 5 units. Another example would be if I decided to go outside and run, I could either run 1 mile to the north, or I could run 1 mile to the south. It doesn't matter which direction I'm running, I'm going to run a total distance of only 1 mile. Your fitness tracker will never say, oh, well, you ran negative 2 miles today. It just says 2 miles. And then the direction in which you ran is entirely separate from the distance in which you ran. Same thing with the absolute value of a complex number. So absolute values of a complex number take on the form, the absolute value of a plus bi. And in order to calculate that distance, it looks very similar to the Pythagorean theorem. So we're going to take the square root of a squared plus b squared. So your real component squared, your complex component without the I squared, all taking the square root. So it really is a squared plus b squared equals c squared, and it has solved for c. And the reason is, if I plot that point, I've left this should not be a minus sign, or a comma, this should be a minus sign. If I plot that same point from the earlier example, I have a vertical distance of 3 units from my real component. I have a vertical distance downwards 2 units from my imaginary component of my complex number. And my distance is a measurement from the origin. So my point lies right here, and the distance starts from that point and goes from the origin directly to that point. So it does make a right triangle. So that is where we can use that absolute value to come up with your distance. So if we're looking at this, this is your A, your B, and essentially your C value, because this is a right triangle. And that is how we derived that particular formula for the absolute value of BI, because it is a distance, and we're working with right triangles. So if I was to work this out, I would have the absolute value of 3 minus 2i is equal to the square root of my a value, which is 3 squared, plus a negative 2 squared. So just be really careful with your signs, as you can see. 3 times 3 is 9, negative 2 times negative 2 is 4. That gives me a grand total of 13, and so the distance, or my absolute value of the complex number, or distance from the origin, is the square root of 13. 13 is a prime number, so it's already in its most simplified form. If it was a number that was not in its simplified form, we would absolutely simplify that down, much like we did on an earlier example. So I do have 2 practice questions. You can pause the video if you want to and try these. The absolute value of negative 5 plus 3i, and the absolute value of 6i. If we were going to try the first one, I would start by setting it up with the absolute value symbol. So negative 5 plus 3i, so the absolute value is equal to the square root of a squared, which is negative 5 squared, plus b squared, which is just the 3, not the I. Negative 5 times negative 5 is 25. 3 times 3 is 9. And that gives me a grand total of the square root of 34. Now, in this particular question, or in this particular value of 34, I want to just double check and see, is this already in simplified form, or do I need to continue to simplify the number 34? So I'm going to break it down. 34 is even, so I know that there is absolutely a 2 as a factor. So 34 divided by 2 is 17. 17 is prime, so I'm only left with the numbers 2 times 17. There are no sets of twins in there. There are no perfect square values, and so my final solution is the square root of 34. That is in its most simplified version. Let's try number 2, just 6i. If I was to rewrite this using an entire a plus bi, so using a complete form of complex numbers, I do not have a value for a, and so in this case we could also rewrite this as 0 plus 6i to assign a value for a. So the absolute value of 6i is equal to the square root of my real component, which is 0, and my imaginary component, which is 6 squared. 0 times 0 is 0. 6 times 6 is 36. So it gives me a grand total of 36. And the square root of 36 is 6. And that's it. So working with complex numbers, they still work in our four major operations of adding, subtracting, multiplying, and dividing. And in this particular lesson, we're only looking at adding and subtracting, understanding what these foundational skills are before we begin to apply them to some higher level operations to include multiplying, dividing, working with conjugates, and things like that. When we're working with complex numbers, we are going to either add or subtract them by combining like terms. And so we are going to be combining our real term, our real parts, with our imaginary parts. And we just want to be very careful because in these particular examples, they are written in the correct form of a plus bi, but sometimes you could have them where they are maybe backwards. So for example, 4 minus 3i plus 2i plus 3. Notice that the second set of parentheses here is not written in the correct form. So just making sure that we're getting in the habit of not assuming that the first numbers get added together and the second numbers get added together, because in this case you would be trying to add real and imaginary pieces of information, and that can't be done. So just kind of starting those habits early, training our brains to slow down for just a minute and look at what's going on. So in this particular example, I have my real component of 4 plus 3, and I have my imaginary components, negative 3i plus 2i. So when I combine like terms, 4 plus 3 gives me 7, and negative 3i plus 2i gives me negative 1i, which is just written as I. So my solution here is 7 minus 1i. The same works when you're dealing with subtraction. A lot of times people will take that subtraction symbol and distribute it in, which is totally okay, and then rewriting the entire problem so that it's just dealing with addition. So distributing that negative sign in, totally okay, totally perfect. Would even recommend myself, but in this particular problem, I do things just a little bit different because sometimes I don't remember to take my negative sign out. It's just my brain and how my brain functions. So here are my real components. So I have 5 minus a negative 2. And the reason I do this is it's easy for my brain to comprehend the double negative and not lose it if I'm trying to distribute values in. It's just a me thing. And then my imaginary components, negative 3i minus a 4i. So when I begin to combine like terms, 5 minus a negative 2, I've got a double negative, making it a positive. So 5 plus 2 is going to equal 7. And negative 3i minus 4i is going to equal a negative 7i. I write it in standard form, and that is it. Voila!